I'm Antonio Sella, and in this video we're going to discuss equilibrium and stability of the Phugoid dynamics of an airplane. In previous videos we discussed the physics of the Phugoid, and in this video we'll analyze if there are equilibrium points and whether those equilibrium points are stable. Indeed, if we simulate this Phugoid mode, it seems that this converges to an equilibrium, in particular level flight, and that such level flight is unstable equilibrium. Well, as we have the equations, our goal is to formally analyze such ideas. If we recall the equations, they were made under some assumptions: planar movement and a weather-vane aircraft that instantly aligns with airspeed at a fixed angle, which, replacing lift and drag by quadratic expressions on the airspeed, gave rise to these two equations governing the dynamics of the airspeed and the path pitch angle, and we are assuming that path angular speed is the same as body angular speed in Phugoid mode. Note that we will not consider that thrust depends on airspeed, because if U depends on airspeed and it's not constant, then that might influence stability analysis and Jacobian's stability derivatives we are going to compute later on. In particular, in constant power propeller engines, this may be the case, but we will neglect these issues for simplicity, and we will assume that thrust is constant to whatever the pilot wishes. Okay, so let us compute the equilibrium points. The theory is well known. A constant solution will have its time derivatives equal to 0, so solving for this now algebraic equation will give me the equilibrium points of the ordinary differential equations. So good, let's place 0 there. So we have these equations, and I can also clean up if so wished, multiplying by m and airspeed in the second equation to get this sort of cleaner way of expressing the equilibrium equations. And at the end, well, we have two equations and three unknowns. So if we know one of them, we can solve for the other two. We will now discuss some particular cases to get an intuition of the meaning of this and compare with simulations. First case is glider, 0 thrust. If I set this to 0, this disappears, and then if I divide one equation by the other, mg and v squared disappear. So I get this expression, and also squaring the equations and using the fact that sinus squared plus cosinus squared is 1, I get an expression for the equilibrium velocity that can also be understood in physical terms, because in my glider, if equilibrium is reached, lift and drag, which are orthogonal, must compensate weight so that the net force is 0. Well, anyway, these are the equilibrium values for a glider. Also, if I get the angle, then it's trivial to get the speed, and once I get this speed, if I replace it there, this will be this expression. So as theta is assumed known, then I can trivially get the thrust, and indeed, here we have the result. So for instance, the desired pitch angle of 0 gives me the thrust and the speed of level flight in equilibrium. Note that, for instance, thrust to keep level flight is the weight times the drag to lift ratio. Also note, for instance, that increasing lift with flaps makes equilibrium speed to be lower. The needed thrust will depend on whether drag to lift ratio changes significantly or not when deploying flaps. A third way of getting the equilibrium point is solving for angle and airspeed when thrust is given. In that case, force balance in equilibrium is the same here, but now I push with u, so the tangential component in this force balance is u minus t instead of the pure drag. So we get this balance, and then replacing this by a lift coefficient v squared and replacing drag by drag coefficient times v squared, we get this. And now, taking this square and operating, we get this equation. So if thrust is assumed known, then my unknown is airspeed. And this is a biquadratic equation, so I can solve for v squared. And depending on whether this thing inside is positive or negative, we will have real solutions for the speed or not. And of course, we are only interested in the positive real solutions for v squared, so I can later on take a square root. So, looking at this with care, we can conclude that if this happens, then we'll have negative things inside the radicals, so there will be no real solutions. The Phugoid mode will not reach equilibrium. And if we are in this interval, we will have two positive solutions giving rise to two different airspeed and equilibrium angles. Well, the best is to see it in MATLAB. So if we execute some code, which you can download from the description, I am setting a lift to drag ratio of 5, just inventing things. So the blue line in this plot tells me the equilibrium airspeed given the angle. My range of angles included negative things because the equilibrium angle for zero thrust is negative. It's this thin vertical blue line at this angle. Level flight is zero pitch. It gives me the maximum airspeed. And then as I get to the vertical, the equilibrium airspeed dips down to zero. And just in case it's of use to me, I have also drawn in red the horizontal component of the airspeed, so that would be the advance velocity of the aircraft, and the vertical component of the airspeed, that will be the climb speed. Of course, assuming that there is no wind, and also this is the equilibrium airspeed, but such an equilibrium may be unstable. We'll see it later. In this second picture, we have the plot of the thrust divided by weight, specific thrust, to achieve equilibrium giving some pitch angle. So this is the zero thrust, achieving equilibrium at the negative angle, glider descending. This is the thrust for level flight, so lift to drag is 5. Then this is the inverse, 1/5, 0.2. And then when equilibrium thrust exceeds the weight, then we have two different angles giving me a solution, and there is no equilibrium if thrust is above a given maximum value. So these plots confirm the theoretical formulas here, and of course those here. So good. Then we have this idea of the equilibrium point. Next thing is stability. In order to assess stability, if we assume constant thrust, then we must linearize this, taking partial derivatives Jacobian times incremental variables. This thing will linearize to cosine times theta. This green theta is in incremental coordinates. The red thing is just a constant once I substitute the equilibrium point whose stability I'm analyzing. This will be the linearization of the quadratic function of the speed. Again, green v is in incremental coordinates. This expression depends on two variables, so I will have the partial derivative with respect to theta times the increment of theta and the partial derivative with respect to the airspeed times the increment of airspeed, and then this L divided by m times v is linear, so linearization is unchanged. Well, this is the linearization that I just copied there as equations 1 and 2. And now it happens that this thing here is equal to L divided by m, because this was the equilibrium equation in the normal coordinate, and operating we get that. So replacing this here and expressing the equations in normalized matrix form, we get this final expression for the linearized module at a given equilibrium point. So the eigenvalues of this matrix will tell me whether this equilibrium point is stable or unstable. If the real part of the eigenvalues is strictly negative, we will have stable fugoid, otherwise we will have unstable fugoid. So if I tell MATLAB to build this matrix and compute its eigenvalues with the equilibrium points I showed a while ago in my lift to drag 5 example we were analyzing, we have in this plot in yellow the imaginary part of the eigenvalues of the poles, and in red and blue the real part. And up to 67.5 degrees, the poles are actually a pair of complex poles with coincident real part. So this is why red and blue lines coincide. So we have oscillations until this point, and then real exponentials, non-oscillatory from that angle onwards. But the important thing is whether the real part is negative or not. Then we see that at sort of 22 degrees of climbing, the real part crosses zero, so the fugoid mode will be unstable from that point onwards. If equilibrium angle is below 22 degrees or descending, the dynamics is stable, but if we push too much, dynamics will be unstable. The plane will climb in an unstable way. So this 22 degrees regarding thrust means that in this case, a thrust above sort of 55% of the aircraft's weight will render the fugoid mode unstable. If I now simulate this thrust, then I will be close to the stability limit. So here we have a climbing, which is stable, but not so if I increase to 60% specific thrust. We see oscillations increasing. To end the presentation, we will now discuss an interesting particular case, which is level flight. In level flight, sinus is 0 and the cosine is 1. Then this is the matrix whose eigenvalues characterize level flight stability, and then the characteristic equation arises from the determinant of this matrix. So, carrying out that determinant, we get this. And in level flight, we have this identity because lift force must equal weight, both are vertical in level flight. So substituting that, we get this characteristic equation in terms of the equilibrium airspeed, and as both coefficients are positive, it will be stable. And if you know this normalized, natural frequency and damping coefficient way of representing second order system, if you don't just forget about it and think on, okay, I can compute these eigenvalues, we did it in MATLAB, look at the code. Anyway, if you know this representation of second order dynamics, the square root of this is called natural frequency, and it's inversely proportional to the equilibrium airspeed. And replacing this natural frequency here and equating to this coefficient, we get that the damping coefficient is proportional to drag to lift ratio in level flight. So if my plane is aerodynamically efficient, low drag, high lift to drag ratio, then this level flight is only lightly damped, so it will be an oscillatory mode that takes a lot to stabilize. Indeed, if I simulate a plane with lift to drag ratio of 30 in level flight, if I start close to the equilibrium, then it's okay, but if initial conditions are not close to equilibrium, then oscillations take a long time to dampen. So we will conclude here. In this video, we have analyzed the Phugoid equations, in particular the equilibrium points and the stability of such equilibrium points. We saw that gliding with no thrust and level flight are stable, but climbing is unstable from a given angle onwards. We also saw that efficient planes have a Phugoid mode in level flight, which is stable but very lightly damped, so Phugoid oscillations may take a lot of time to disappear. Simulations have confirmed our theoretical results. So we finish here. Thanks for your attention.